Now we're recording, and I need to share the screen. Okay, so this is the stuff that we have only done remotely. Okay, so this is probably where you are going to have questions. We'll start with heat and thermochemistry. You guys, at some point, hopefully in grade school or middle school, you talked about all the different kinds of energy, and one type of that energy is heat. And heat energy is different from temperature. Temperature is a measure of the average kinetic energy of the particles, whereas heat is the total energy. So instead of just looking at how fast particles are moving on average, you're taking into consideration the mass of the thing. So you end up, and we use Q, and I don't know why we use Q. Someday I'll figure it out. We use Q for heat. We use M for mass. C is the specific heat. You know that different things heat up differently. That's why you use a wooden spoon when you're cooking on the stove instead of a metal spoon, because the metal spoon can heat up. The wooden spoon is a insulator. It doesn't conduct heat energy. And that would be a specific heat. That's a property of that substance, that it doesn't conduct heat. And then delta always means change, and it's just a change in temperature. So those are pretty easy to, and I actually probably have examples here. Those are pretty easy to calculate. If you're putting heat in, it's going to be a positive outcome. If heat is being given off, it's going to be a negative outcome. Positive means it's endothermic, because heat is going in. I don't know if you can see. I keep teaching with hand gestures, even though I don't even think you can see my hands. And exothermic means the heat's being given off. Okay. And I think I sent you guys this worksheet. And anybody have any questions on calculating heat exchange? You guys good with this?
Yeah.
Okay, so this is basically if you have something warming up or something cooling down. It's not a chemical reaction. When we start to talk about a chemical reaction, we have to talk about enthalpy. Enthalpy, here's an example of standard enthalpies. Enthalpy just means heat, basically. Enthalpy is the energy. We can't measure the energy directly. We can only measure the change in energy, how a system's energy changes as the reaction goes. For whatever reason, we call it enthalpy, and we use the letter H. And I think the letter H is Greek eta, if I remember right. And so I'm sure that there's a connection there why we use H for enthalpy. But so if you have, let's see, did I put a enthalpy diagram in here? Here we go. So these values, and you'll be given the values you need. You won't have to look them up on a table. But these values are all changes in heat or changes in energy when this substance is formed. So when aluminum metal is formed, we have no change in energy because aluminum is its basic state. It's an element. So there's no change in energy. But if we form aluminum chloride, we are going to produce 705 kilojoules of energy. It's negative, so it's going to give off the energy. And here, let's find a positive one. These are all elements that are ions and stuff that are positive. Here we go. Ethene, which is C2H4, is a positive. I don't know why there's a difference between this guy and this guy. Oh, because this guy's ethine, C2H2, C2H4. That's my issue. Those are both positive, meaning in order to form ethene and ethine, you have to put energy into the system. So when you have a heat, when you ask, and this is a question, if it asks you which one of these shows you the proper heat enthalpy of formation for a compound, the enthalpy of formation means it's coming from its elements. So in this example here, magnesium carbonate, you would have magnesium plus carbon plus oxygen producing magnesium carbonate. If for sugar, it's carbon plus hydrogen plus oxygen. So when it asks you for heat of formation, that's what it's asking for. And that little F means formation. Okay? So you'll have a question that'll be like, well, you'll use those enthalpies of formation. What would you use them for, you ask? Well, that is when you have to determine the enthalpy of a reaction. And when you determine enthalpy of a reaction, you do products minus reactants. Okay, and here are our products. I'm going to change color for my reactants. I should have written this in blue. And so then we have to look these up on a table. Okay, so starting with our products, 4NO, and let's see, do I have them given in here or do I need to look them up? I'm going to have to look them up. And that was right here. NO, we look down to nitrogen. And again, you aren't going to have to look it up on a table. 90.29. Where am I? Enthalpy of formation. And it's positive, so you just write it in there as positive. And 6 waters. And water, and it's a gas. That's important because water could be a liquid. Water's going to be under hydrogen. Here is water as a liquid, already underlined, negative 285.83. And then I'm going to change color. We're going to look up our reactants. We have 4 ammonias that are gases. Ammonia is going to be under nitrogen, negative 4590. Plus 5 oxygen as a gas. Oxygen's an element. You can look it up just to make sure, but it would be 0. And now you just do the math. So the hardest part of this is remembering products minus reactants. Okay? And there are on those heat worksheets examples of those. That's not, because that's heats of formation. These titles are bad. This should be enthalpy of reaction. All right, well, those examples that say enthalpy of formation should be enthalpy of reaction. I need to go in and fix those. That would be examples. And I worked some of those in some of the online videos. Okay, so if I go back to my review, so far we've talked about this guy. We've talked about the definition of enthalpy. We talked about enthalpy of formation and enthalpy of reaction. So questions, do you want me to do some more of those? How do you want to proceed?
Can you go over the first thing again?
Q equals MCAT?
Yeah.
Sure. All right. So Q means heat, M means mass, C means specific heat, and those are numbers are assigned. We'll have to look those up. And delta T means temperature. So let's look at number 7. Q equals MCAT. It gives us energy. So we're going to sub in 186,000 joules. It does not give us the mass. That's what we're going to solve for. It tells us it's copper. Copper is 0.387 joules over grams degrees Celsius is the units for that. Temperature change, it doesn't give us a start and end, but it tells us that this is the change. It's 285, and it increases, so it's positive. So now we just solve for mass. So we would want to divide both sides here by 0.387. So those would cancel, and that would solve for mass. 186 divided by 0.387 divided by 285. So the mass of the copper, if I did my math right, is 1686 grams. Yeah. Okay. That help?
I'm good now. Yeah.
You want another one?
No, I'm good.
Okay. All right. So we're okay with the enthalpy of formation, have to come from the elements. That's important. And an enthalpy of reaction, you're going to use formations, and it's products minus reactants. Okay?
Yep.
All right. Bond energies is a little bit different, and I don't like teaching it, or I have always taught it in there. It's not the way, it's in a different section of this book that the online stuff was ordered in, so I actually taught it last. But for bond energy, if you're talking about bonds themselves, what we're talking about is if we have this guy right here, number 2. Every time we break a bond, we have to put energy into it. It's like breaking Legos apart, okay? So if we break the CH bond, CH is 413, and there's 1, 2, 3, 4 of them. There's 1 fluorine, which is 155. And there's a double bond carbon-carbon, which is 614. So you would add those guys up. Now, to make this, we're going to put the Legos back together. That's going to release energy. We have 1, 2, 3, 4 CH bonds. We already know that that's 413. So really, this is redundant. We could cancel those out. We have 2 CF, which is 485. And we want 1 carbon-carbon, single bonds, 348. And what we would do, we put energy into this, and then we got energy out. We don't worry about signs. We just take this minus this. But energy being given off is subtracted. So you're, in this case, these are reactants minus products. For bond energy, it's reactants minus products. For energy of formation, it's reverse. okay? And you could calculate a reaction doing bond energies, or you can do it the other way. They both work. But the bond energies, you have to count all the little bonds up. I don't remember seeing one of those on the final, so I think we're probably good with that, but I'm going to hit it just in case my memory isn't good. The last thing is Hess's law. Again, I don't remember seeing one of those on the final, but we're going to go through it anyway. Hess's law is just like a big puzzle. And I actually have these reactions written out on cardstock that's laminated, and you can flip them over and it's the reactions at the reverse on the other side, and you can move them around, and it actually makes Hess's law fairly easy to teach. But what you're going to do for Hess's law is, let's do the heat worksheet one so we don't have one that's already marked up. Okay. We want to recreate this. So I'm going to rewrite it over here. Over there. Now, of course, because we're smart, we know that we could go look that up on a heat of formation table, but for whatever reason, we can't do that with this reaction. So we're going to do this a different way. And this wouldn't be a heat of formation because, no, this one would be, but we're going to use these two over here, okay? So the first thing we have to do is we have to find carbon by himself. And the first equation has carbon by himself. The carbon's on the reactant side, so we don't have to do anything to that equation. This is a heat of formation because to make CO, you would only use half of a mole of oxygen. And that heat of formation is negative 110.5 kilojoules. And we've got some oxygen here. Now, CO2 is in this second equation, and it's on the right-hand side. It's on the product side. That's where it needs to be. So we're going to copy that over here, just like CO plus 1/2 O2 gives us CO2, and it's negative 283.0 kilojoules. Okay, now we're going to put them together. So we're going to add everything on the left here. Carbon plus 1/2 oxygen plus 1/2 oxygen plus carbon monoxide. And the other side is going to be carbon monoxide plus carbon dioxide. What do they tell you to do in math when you have an equation like this? They tell you to combine like terms. Do we have anything that's the same on the left and the right? Yes. The carbon monoxide is the same on both sides, so we can cross those out. We can combine like terms. 2 halves makes 1. And we have the same equation up here. Okay? We didn't have to reverse any equations, so we don't have to change the signs of the energies. We didn't have to multiply anything or divide anything. So all we have to do is add those two together, which would be 283.589 negative 393.5 kilojoules. Okay? That's all Hess's law is really doing, is just adding things together. Let's look at the next one. Let me erase this. Well, no, I don't want to erase it because I want to give it to you guys. I'm just going to make it smaller. Maybe. There we go. Okay, let's do the next one. This is what we want to make, XeF2. And I'm going to go ahead and rewrite it over here. Plus F2 gives us XeF4. Okay? We have two equations we can use. Do either one of these have XeF2 in them? We're matching this guy up. Is he on the reactant side? Is he on the left side of the equation? No, he's not. So we have to reverse this reaction. So instead of writing xenon plus F2, we're going to start with the products. And we're going to get F2 plus xenon. And then our energy was negative 123, but because we reversed it, it's now positive 123 kilojoules. Now we've got an F2, but it's on the right-hand side, so we're not done yet. The other equation gives us more F2s on the left, and it gives us XeF4 on the product side. So we're going to do Xe plus 2F2 gives us XeF4. We didn't change anything, so it's still negative 262 kilojoules. Now we'll mush them together. So we'll bring XeF2 down, plus Xe plus 2F2 plus F gives us NF2 plus Xe plus XeF4. These two will cancel out because they're the same on both sides. We have one fluorine on the right side, 2 on the other, so that guy cancels out, and this guy becomes 1. So if I get rid of everything I crossed out, I now have the same equation that I started with. So I would just add those two together. Questions about that?
I'm good.
Okay, excellent. Because that's the hardest thing, in my opinion, of the whole deal. All right, so we've done that guy, we did that guy. Gases. You guys know things that affect gases. Gases is actually something that I covered fairly well in Gen Chem. The most important thing, you have to change it to Kelvin. Up here, because you're dealing with changes in temperature, and Celsius and Kelvin are the same size, it can either be in Celsius or Kelvin. But if we're talking gases, Kelvin, 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 Kelvin. Has to be changed to Kelvin. All right, we have 3 relationships, and they all build together. We have Boyle's relationship, which is inverse. So if you multiply your pressure and your volume of a something, and then you change it, and you multiply the new pressure and volume, they're going to equal each other. They're going to equal a constant, which is going to be each other. So this is the relationship, and if you use the letter N as a constant, which is confusing because N means moles. But this is, or no, you'd use K as a constant, I think. You can use either one. All right, so this is Boyle's law. Boyle's law is the only one that's inverse. One goes up and the other goes down. That makes sense. If you squeeze something, the volume goes down. So that one makes sense. The second law, Charles' law, is the relationship of volume and temperature. So if I cross this guy out, you get Charles' law. Undo that. Volume and temperature equals the new volume and temperature. And Gay-Lussac's law is right here. The 3 of these fit together to make PV over T equals P2V2 over T2. Okay. The fourth thing that affects gases is how many particles you have. Hang on, I'm going to shut my back door because they're mowing my yard. All right. The fourth piece is the number of particles. Stop and think about it. If you blow into a balloon and you increase the particles in the balloon, it gets bigger. So the number of particles is directly proportional to volume, which means we can put it under volume in this. So these are our basic gas laws, okay? If you take 1 mole of a gas at what we call standard temperature, which is 0 degrees Celsius, 273 Kelvin, the volume of that 1 mole of gas at STP, standard temperature and pressure, is 22.4 liters, and the standard pressure is 1 atmosphere. If you multiply those out, you end up with 0.0821 liters times atmospheres over moles, that's mole, times Kelvin. That is what we call the ideal gas constant. And it is simply a way to compare, rather than before, remember I had PV equals P2V2 and PT equals P2VT2, and you can put all those together. Rather than having to have a before and an after, this takes place, this is what you're going to compare it to. So this is the after, if you will. And we call that R. So we get PV equal over NT, that equals the ideal gas constant. You can rearrange numbers algebraically, and this is the ideal gas law. Now, to figure out what you're going to use in your ideal gas law problem, you have to look and see what's in the problem. For instance, I'll pull up the gas, here, some gas problems from honors. I don't have a review on here, never mind. All right, so if we look at these, this problem, yeah, that's stoichiometry. I haven't done that yet. All of these are ideal gas law because they all have, if you look, they're either going to have mass or volume. Let's work number 3. We already know it's PV equals nRT. It tells us we have a mass. It tells us volume. It tells us temperature. It tells us pressure. What it's asking for is molar mass. Molar mass is grams per mole, and we have grams. So what do I need to solve for? I need to solve for moles. Well, that's easy. PV equals nRT. Did I just mute that? No, I didn't. All right. PV equals nRT. If we're going to solve for N, divide both sides by RT. So you take your pressure, 0.980 atm. Take your volume. Can I use milliliters? No, got to switch to liters. So 0.0725 liters divided by R. That's the one I just figured out, 0.0821. That'll be given to you. You don't have to memorize it. It'll be part of, I'll give it to you. I will give you guys, send you guys an email with the formulas you need. And the temperature was 68. I have to add that to 273, 8, 9, 10, 11, 341. So if I plug those in, 0.98 times 0.0725 divided by the ideal gas constant divided by, we end up 0.00253 moles. What's my original question? It asked for molar mass. We have grams. So to get molar mass, I'm going to put 0.0207 divided by 0.00253. I don't think I did that right. 207 divided by 0.00253 gives us a molar mass of 81.8 grams per mole. I think it's more straightforward than that. I don't think you have to figure out molar mass. That's kind of an oddball one to have chosen. Okay. Questions about gas laws?
Nope.
We talked about gas laws, an ideal gas law. Okay. Oh, I didn't put Dalton's law of partial pressure on here. All right, let's do Dalton next. And we need to do stoichiometry. That's not on there either. All right. Okay. A sample of gas is collected over water. Let's talk about gas being collected over water. If you have a gas, I think actually I have this in a nice picture in this. If you have a gas being collected over water, in this space, see the gas was generated over here, it bubbled through. In this space, you're going to have mostly that gas, but you're also going to have water vapor. Okay, Dalton's law of pressures, partial pressures say the parts add up to the whole. So you've got pressure out here pushing down, and that is going to be equal to the pressure put on the sides of the container from both the water molecules and whatever the gas was that you made. So you have to be able to look up partial pressures. And again, they're going to give you this. You're not going to have to look it up. But if you were to look it up, the table looks like this. Okay? The problem I gave you says we want to know the pressure of the gas at 35 degrees. So first we got to look up water at 35 degrees. Water is 41.175, and this is in millimeters of mercury, so we're going to have to do a conversion. So we know that the total pressure is equal to the pressure of the water plus the pressure of the gas. We just said, and I've already forgotten because it's my brain, 41.175. And we know that the pressure outside of the atmospheric pressure, the total pressure, is 1.1 atmospheres. So here's our problem. One of them is in atmospheres, one of them is in millimeters of mercury. We got to change one of them. Doesn't matter which one we change. 1 atmosphere is equal to 760 millimeters. So I'm going to change this guy. And I'm going to multiply them by 1 atmosphere over 760. 41.175 divided by 760. Now my pressure is 0.0542 atmospheres. Now I solve for the pressure of the gas. Okay. The one above it gives you the 3 gases, and it tells you you've got carbon dioxide, nitrogen, and oxygen. So the total pressure is equal to the pressure of the CO2 plus the nitrogen plus the oxygen. It tells you the total is 1 atmosphere. The carbon dioxide is 0.27. The nitrogen is 0.53. And you just solve for the pressure of the O2. Again, straightforward. That one I feel like is, once you've worked a couple, you're good. Let's talk about effusion. You've all seen a balloon that has gotten smaller over time. Why? The particles, if the particles get cooler, they're going to get smaller because of Charles' law. Volume and temperature are directly related. Cooler temperature, cooler volume. In fact, you could get a balloon and put it in your freezer and you'll notice that it's gotten visibly smaller, and you take it back out, it poofs back up. But over time, balloons have teeny tiny holes, and gases are teeny tiny, and those gases can get out. So if you've ever gone to Party City, they'll put something called Stay-Flow or something like that, although that's the name of starch, so it may not be the right name. But they'll put something in the balloon before they blow it up that'll help to seal off those little particles. When a gas goes through those little particles, that is called effusion. The bigger the thing, the slower it's going to be. That's all you need to know about effusion. So the question is going to be something to the effect of, which will effuse the fastest? Figure out the lowest molar mass. Which will effuse the slowest? Figure out the biggest molar mass. There's a whole equation involved where you got to do the mass compared to the velocity is equal to the velocity of the second one compared to the mass of the second one, and you do the square roots. You don't need to do any of those calculations. There were calculations like that in the online stuff that they had you doing, but all you need to know is fusion big equals slow. So we've done that. All of these are considered for gases at normal, relatively normal pressures and temperatures. Okay? These are all based on the idea that gases are in constant motion, and they are moving so fast that they don't come in contact with each other. When we talked about water molecules, I have the water molecule example at the front in the picture where they've got the magnets and they're attracted to each other, intermolecular forces. Well, if they're moving fast enough, do they have intermolecular forces? No, even if they're polar, they don't have any intermolecular forces because they're moving so fast. Okay? What's going to happen though if you cool those guys off? If you're cooling them off, they're going to get closer together because lower temperature, lower pressure, lower volume, and they're going to be moving slower. So can intermolecular forces act on them? Yes. So if you have really cold temperatures, ideal gas laws don't hold up. The other thing would be if you have really high pressure. If you have really high pressure, you're going to have a really small volume again. So basically, it all comes down to small volumes. High pressure, the particles are going to be close together. It could be a small volume with low pressure, though, and then it wouldn't affect it. So high pressure or low temperatures are going to create tiny enclosed space, and those particles will interact with each other and IMFs will happen. Okay, so that's all that means. And this is going to be a question like, what's an example of gas that wouldn't obey normal gas laws? Okay. All right, let's do stoichiometry, because that's the one thing we didn't do. Did we do that with heat? We didn't do that with heat either. We didn't talk about that with heat either, did we?
No.
All right, because I left that off of there. That's just so I remember to put it in. All right, let's go back and we'll do the stoichiometry of the heat. It's just using mole ratios again. All right. Enthalpy stoichiometry. Let's use the heat worksheets because we got them already. Okay, here's our question. This is an enthalpy of reaction. Okay. It's also enthalpy of formation because we're making a sulfur trioxide, but we're making two of them, so it's not a heat of formation. But anyway, we know that if we make 2 sulfur trioxides, we're going to release 791.4 kilojoules of energy. If we start with 6.44 grams, how much will we release? Well, if we make 2, we had to start with 2 moles of that, right? 1 mole of sulfur is 32 grams. 2 moles of sulfur would be 64 grams. So what we're going to do is we're just going to do some more stoichiometry. First, we have to change them to moles. Everybody knows how to do that. Grams divided by the molar mass, which is 32 grams in 1 mole. Now we're in moles. 6.44 divided by, I'm going to do this in segments. So we have 0.20125 moles. Okay. What's our normal number that we're going to use to produce this? We're going to use 2. So we're going to multiply by the ratio. Here's where it's different. We're not going to compare to this guy. We're going to compare this to this. What goes on the bottom? Our known amount. We know 2 moles will react and form negative 791. So now you just do the math. Okay. Next one. 4.72 grams of carbon. How much heat will that release? So 4.72 grams divided by 12 grams per mole. And then we're going to multiply by the ratio of the coefficient to the energy. Coefficient for carbon is 1. The energy is 393.5. And you'll get energy. Okay? If you got one like this, this guy is giving us energy and it wants to know mass of propane. So we're going to work backwards. We're given 76,000 kilojoules and we want to know moles and then grams. So before we multiplied by the coefficient under the energy, guess what we're going to do this time? We're going to multiply backwards. Come on, come on. So the energy is that, what's the coefficient in front of the propane is a 1. That's going to give us moles. And then we will multiply that by grams per mole of propane. So 76,000 divided by 2200, we get, and this is, it says it's producing, that means it's being given off. So negative divided by negative is positive. 34.5 moles of propane times the molar mass of propane, which would be 3 times 12 is 36 plus 844. 1520. If I did my math right. Okay. So that's stoichiometry of heat. The only difference is instead of solving for moles on the other side, you're going to solve for energy. So your mole ratio will be ratio of moles to energy. Okay. Stoichiometry of gases. For stoichiometry of gases, we have to use oh, I didn't want to paste that. I wanted to delete it. What am I pasting? Okay. So let's look at the problem. We need to figure out what is known, or I'm going to use yellow for known. We know that we have 55 grams of oxygen We know the pressure of the oxygen and the temperature of the oxygen. So can we find moles if we know all that? Yes, we can. We can use the ideal gas law. Ideal gas law, PV equals nRT. Divide both sides by RT. I can get number of moles. No. We've got grams. That's what we need for numbers of moles. Let's start this again. We're still going to use PV equals nRT. But we know this. We need a volume. Okay. I'll show you why. So volume is the piece we're missing from oxygen. So V equals nRT over P. So 55 grams per mole of oxygen divided by 32 grams per mole gives me moles times the ideal gas constant times temperature, which was 85, 273, 358 Kelvin, and divided by pressure, which is 12.4. So I'm going to do the math. Divided by 32, 0.0821 times 358 divided by 12.4. You get 4.38 liters of oxygen. Now, we're going to use stoichiometry. Okay. Let's see. How many liters of water? So we're making water, and we're making it from oxygen and hydrogen. If we balance that, we need a 2 there and a 2 there. Okay. We know we have 4.38 liters of oxygen. We want to know how many liters is the hydrogen going to be, or the water. So look at your mole map. If you know volume of a gas, and this should be divided by, not times. If you know volume of a gas, how do you change it to moles? Well, 1 mole of gas has a volume of 22.4 liters. So you can take volume divided by 22.4 liters per mole. But look what happens on the other side when you're going back to volume. You multiply by 22.4 liters per mole. So only when you're working with volumes of gases, as long as pressure is staying the same on both sides, temperature is the same on both sides, you actually can just go straight into the mole ratio. You don't have to convert. So this problem here, 4.38 is our known. What's my ratio of our known to unknown? 1 to 2. So we would have 8.8, so close to 8.8, 8.76 liters. Okay. Let's see. Let me pull one off of honors just for something different. Let's do number 6. Dinitrogen monoxide can be prepared by heating ammonium nitrate, which decomposes according to this equation. What are we solving for? We're solving for mass. So we aren't going to get to go liters to liters, but that's okay. We're solving for mass. What are we starting with? We're starting with a volume. It doesn't tell us anything about the gas. It doesn't tell us the pressure. So we're going to assume it's at STP. So look back at see down here? Yeah. We're starting here. What's the first thing you're going to do? Remember that I made a mistake on this. This should be divided by. So the first thing we're going to do is take volume divided by 22.4 liters per mole. So our volume is 0.25 liters. We're going to divide by 22.4 liters in 1 mole. What is my ratio of dinitrogen monoxide to ammonium nitrate? It's 1:1. Now we have to change molar mass. Okay, Google, what's the molar mass of ammonium nitrate?
The molar mass of ammonium nitrate is 80.04 grams per mole.
I love doing that. 0.25 divided by 22.4 times 80.04, 0.893 grams. Okay, so questions about stoichiometry. We'll do gases because we just talked about that, and then I can pop back to the heat.
I'm good.
You're good?
I'm good.
All right.
I gotta log off. I gotta go to work.
Okay. We're almost done anyway. All we have to do is triple point. So you should.
Okay, cool.
And it's being recorded.
Gotcha.
Have fun at work.
I will. Bye.
All right. Okay. So we got, let me make sure you got everything on there. So now we just need to talk triple points. And I'm going to go back to our notes on that, on phase diagrams. This is a phase diagram, and this is all, you're just going to have to be able to read one of these for the test. That's all. Okay. So look here. The triple point is the point where you have solid, liquid, and gas, and that makes sense because they're all touching that. The solid's always going to be the top left corner, the gas is always going to be the bottom right corner, and then the liquid's whatever's in between. Okay, notice how these are different shaped for iodine versus water. And then there's carbon dioxide under that. You get different shapes, but you still have solid in the upper left, bottom in the lower right, gas, bottom, solid in the upper left, bottom in the lower right, gas up here smushed in between. So you've got the pieces you need to know about this. You've got your triple point. You've got the critical point, which is when liquids and gases act like it can't make it become a gas anymore. It's all going to be a liquid. And then as you cross this line, you're melting. If you go back the other way, you're freezing. If you cross this line, you're vaporizing. If you go back the other way, you're condensing. If you cross this, you're going to change from a solid to a gas, which is called sublimation. Go back the other way, and you're depositing. It's called deposition. So that is pretty much all you need to know about those. So, questions?
No?
All right. 1 o'clock good for you tomorrow, Aiden?
Yes.
All right. If you have anything come up tonight, text me. You have my number still?
Yeah.
All right. Text me if you have a question, because I probably won't check email. I'm going to go out and do some gardening. And so text me and I can answer questions.
Okay.
All right.
Thank you.
You bet. See you later, kiddo.
Bye.